Hi, I'd like to go over a method of producing pulse width modulation in the digital domain. I'll review the base 2 numbering system as it applies to register math, and I'll review the characteristics of square waves. I'll end by implementing the scheme in hardware on a field programmable gate array, otherwise known as an FPGA. I'll then use it to drive an LED using pulse width modulation. Alright, so I'm going to use this spreadsheet to help us go over some of the 8-bit register math that we'll need to understand the pulse width modulation. This section I have highlighted is the 8-bit section. In general, unless otherwise noted, the rightmost bit is the least significant bit. The leftmost is the most significant bit. And these are weighted in what is known as a 2 raised to the n format. So the n is the number of bits. In this case, it's zero relative, which is typical, but it's 8 bits. It's 0 through 7. So 2 raised to the n is 256 possible combinations. And the maximum value, if all bits are set to 1, is 2 to the n, and then you subtract 1 from that value. So 256 minus 1 is 255. So that's if all of these zeros were set to a 1. So I'll start off with making a binary 1. So I'll put a 1 in the least significant bit. You see now we have decimal 1. Binary, you can see that bit picked up. Hex, we won't touch on the hex right now, but it's just another way of stating that. So if we wanted to make a 2, just put a 1 here. There's our 2. If we want a 3, we'll need that 2 plus a 1. Or 3. If we wanted a 4, 4 already exists. It's the third bit, or bit 2 being 0 relative. So we can set these back to 0. We'll set this to a 1. There's our 4. Now we want to go to 5, so we need 4 plus a 1. We'll go to 6, so we need the 4 and the 2. When we go to 7, we need the 4 and the 2 and the 1. There's our 7. Now 8 exists on its own as the 4th bit, or bit 3, 0 relative. So we'll set these back to 0. And pick up that bit on its own. Those are 8, 9, 10, 'cause you can see there's a pattern to this. These numbers, you can think of the number, the weighted number is being turned on or off by whether there's a 1 or a 0, whether you have that bit selected or not. All the bits that are selected add together. All the bits that aren't selected, they're basically turned off. They don't count for anything. So let me show you another way of seeing that. So I built this in LabVIEW to demonstrate binary counting, and ultimately how we're going to use it to perform pulse width modulation. So I'll go ahead and start this VI, and this side over here is our counter, and all it'll do is it'll count. It's just going to count up When we get to 255, which is the maximum number that this register can hold, it will overflow and it will start back at 0 and start counting back up again. So I've got the counter delay at a higher value, basically at 1 second, and I'll speed that up as we move along. So here's our 1, 2, 3, 4, 5, 6, 7, 8, 9, and so forth. So that's the same thing we went over in the spreadsheet. I'm going to increase the rate that it's counting. And we're going to get to 255, and we're basically going to overflow and start back over, or starting back over. So I'm going to go ahead and go down to 1 millisecond delay. So as you see, we're flying through to 255, overflowing and back again. This is a graphical representation of the counter value. So the PWM output is this representation of an LED, but notice I've got it set up to be counter value less than the set point. The PWM output is on, but our set point is at 0. So the counter value is never less than 0, so the output is always off. So I'm going to go ahead and increase the set point. I'm going to take it somewhere around the middle, somewhere over here around 125, 128. So now, if you compare it just kind of visually, while the counter value is in this bottom half, it's less than the set point value. The LED is on. But as soon as we cross over and we're greater than the set point, the LED goes off. So if we raise that set point value, we could raise it all the way to 255. And now the counter value is always less than the set point. So the LED is always on, and we can see that in the waveform in the top. We're always turned on. It's never off. So we'll back off a little bit. And you can see we're still mostly on, but we're off part of the time. Looking at the duty cycle here, it's telling us that 78% of the time the counter value is less than the set point. So here we're almost half, you can see. So 49.8% of the time, the counter value is less than the set point, and the LED is on. And you can see this square wave is pretty symmetrical. So now we've only got this small period of time for 9.4% duty cycle where the counter is less than the set point. The rest of this time, it's off. And you can see the representation of the LED is flickering. But it's what really happens with a high enough frequency. It doesn't work as well on LabVIEW, but in real life, if you run a high enough frequency, the LED will appear to be dim because it's never really coming to full brightness. And at a 50% duty cycle, it'll still be dim, but it'll be a little brighter than it would be at 25%. Of course, at 100%, it'll be the full brightness. But one thing I do want to point out, the square wave is always either on or off. So a multimeter will read that it ends up reading the average value of of this DC. So if you put a meter on this at a 50% duty cycle, which is 1/2, you'll read 1/2 of the applied voltage. But in actuality, the voltage is always either, in this case, with an FPGA, 0 volts or 3.3 volts. There is really no in between. But by varying the duty cycle, we change the average. If you were to take this periodic waveform, and by periodic I just mean it repeats perfectly every cycle. You can see where they repeat. And that's how we're able to determine the frequency and period. We can't assign a frequency and period to a waveform that's not periodic because it doesn't repeat on a known interval. But as you can see, this repeats on a known interval. Okay, so I'll move on now and I'll show you the actual physical implementation of what we've described here in this LabVIEW VI. Alright, so here we have a breadboard, and I've got a Xilinx FPGA development board attached to some LEDs. Within the FPGA, I've created a counter register that's 8-bit wide, and I've got a set point register that's 8-bit wide. And then I've got a counter input, which feeds the counter value into the counter register. Then I've got the dip switches, which you can't really see, but they're right here on the development board, and they actually pick up the set point value. Then I've got a LED right here. This is our PWM output, and that will light based on the conditions that were described in the LabVIEW VI. When the counter value is less than the set point, then this LED here will have some value on it based on what value you assign to the set point. So right here we're only going at 2 Hertz. You know, it's pretty slow. I'm going to go ahead and crank that up to 200 kilohertz. So now the LEDs for the counter, they look like they're all just lit, but actually they're still cycling through the same way they were at 2 Hertz, but it's so fast that it looks like they're just on all the time. So I'm going to go ahead and put the 128, the value 128, into the set point register, which is the most significant bit I'll set. So now we're at 50% duty cycle, and we can see that on the oscilloscope as well. And I'll throw in a few of these higher bits, and if you watch the output LED, it gets a little brighter as we go. So I'll go ahead and turn these back off. I'm going to start at the least significant bit. You can see a little tinge of green, very low duty cycle. We'll keep increasing. You see, it's getting brighter and brighter as we go. Then anywhere in between, you've got 255 individual settings for the brightness of that LED based on what value you put in your set point register. The implementation on a microcontroller is pretty similar. You've got a timer, and basically it's driving a counter, just like what we're doing here, and it's comparing the value in the counter to a value in what they typically call an output compare register, but it's a set point register, and the output toggles based on how you configure the PWM in the microcontroller, but you can configure it to do this same thing where its output is on when the counter value is less than the set point. I hope you enjoyed this presentation.